www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, let's get started. And today we'll be talking about non-ideal effects in MOSFET. And presumably so far we had been talking about an idealized version of MOSFET in which several things were simplified. But in real life, there'll be a few things, more things that we would like to add, and in some ways best discussed separately so that you can clearly distinguish between the essential operation of a MOSFET and these additional considerations that are present in every MOSFET and are very important for the operation but are not fundamental to it. So the first topic we'll be talking about is this so-called flat band voltage. I want to define what it is, how to calculate it, and how to measure it from experiments. Then we'll talk about this threshold voltage shift due to trapped charges. Now, we hadn't been talking about charges within the oxide. The oxide we assumed was charge-free. The electric field in the oxide was constant. But in many times, the oxides are amorphous material. Remember, silicon dioxide. These are random material, lots of defects in there, and once charge often gets trapped in there. And that shifts the threshold characteristics, and we'll see how that affects transistor performance. You can see that if you have traps in the oxide, or charges in the oxide, then the charges that you need to balance the inversion charge on the gate would be slightly different. So you can begin to see that there will be some differences. We'll see how to handle that. We'll talk about physics of interface traps as well, a very important consideration, and finally come to some conclusions. Now, just like in bipolar transistor, we use the gain of the transistor. Remember, beta was done as a ratio of the dopings in the emitter and the collector, emitter and the base, and Ni squared for the base and the emitter. And we used to hang our ideas of improving the bipolar transistor performance, or to understand various features, using the gain as sort of the central point through which we relate various ideas. So here I will use this current expression for the current. ID is the drain current, obviously above threshold, using this law to essentially bring together various ideas that we want to think about. Remember that although I have written it as Vg minus Vth squared, Vth of course is the threshold, this square is not always correct, right? The exponent is close to 1 rather than to 2 for modern transistors. So the first thing we'll talk about is the non-ideality of the threshold voltage. Next class we'll talk about the mobility mu naught, and then we will talk about the physics of COX, and then that will come to the conclusion of the MOSFET analysis. Now, the threshold voltage is more than what I have told you so far. What I have told you so far is the V threshold ideal, which is on the first term. That's what I have told you before. But there are these additional things that you haven't seen before. One is this phi ms, that there is a work function difference between metal and semiconductor. That comes in. And then we'll see where that comes in. Then there is this Qm is the amount of charge within the oxide divided by COX. There is this factor gamma. There are fixed charges divided by COX. That also changes the threshold voltage. We'll see how it works. And there's also finally an interface trap. You can see IT stands for interface, and the amount of charge that you have on that interfaces depends on the band bending, vice versa. So we will discuss each one of them, as you will see, separately, and then we can, so that you can get a feel for what these things are. So let's get started first thinking about Just briefly reminding you about what this VTH ideal was. We have done it for last few classes. And then we'll start by talking about this, the phi ms, the metal semiconductor work function difference. So now you remember this picture. This one side is metal, insulator, and the semiconductor is P. One thing I should remind you that in modern transistors, this is how transistors used to be in 1970s, that the first Intel transistor had the metal as aluminum as a metal and 4004. So in 1970s, that has a metal in it and interconnects and others. These days, most of the transistors have for the gate polysilicon, highly doped polysilicon. It's a semiconductor, not a metal anymore. But for this is a strange twist of life in some way, that we have actually gone back to metal now. So the latest Pentium would again have metal. And this is a different type of metal, but again, it will have a metal-related compound over there. Oxide and, of course, semiconductor. And we assumed a hypothetical metal and a hypothetical oxide such that the chi-i's and phi sub m and chi-s all essentially gave you a flat vacuum level. But you know that that's not generally the case, right? For practical material, that's generally not always the case. So this was a special case. And from that, we were able to calculate above threshold, the invert amount of charge induced, mobile charges these are, and that was Cox Vg minus VTH ideal. And what is that VTH ideal? Well, the VTH ideal was phi sub s, and the phi sub s is 2 phi sub f, twice the bulk Fermi level. That's the first term. And QB divided by Cox, that's the voltage drop across the oxide. And you remember that you have to manipulate them a little bit to find that the electric field is related to the bulk charge, and the Cox has in it the X naught, the oxide thickness. So you get that, right? That's the amount of inversion charge that you need if the bands were flat. And in that case, life was very simple. It was flat at zero voltage. So the voltage was flat everywhere. Electric field was flat everywhere, essentially zero, because that's the derivative of the potential, and the charge, derivative of the electric field. So take as a derivative of zero, that remains a zero. So life was good at zero voltage. That is where the transition point was between accumulation. Remember, if you put negative voltage, accumulation. If you got positive voltage, that's depletion first. And that transition happened at 0 volt, idealized case. But in reality, things are going to be slightly different, as you can realize. And also, by the way, the VBI, the built-in voltage, was equal to 0. Because remember, the VBI is essentially difference of the vacuum level on minus infinity and plus infinity. Though those last two materials matter. Flat everywhere, 0 VBI. In reality, of course, what you find that the metal work function, depending on what metal it is, if it's aluminum, copper, or any other material for that matter, you will have a work function, phi sub m. Now, in general, depending on the semiconductor you have, if you have silicon, then you have one chi sub s, or if it is germanium, many transistors these days are germanium transistors, you'll have a different chi sub s. The oxide inside, the oxide could be silicon dioxide, many times these days hafnium oxide, so that chi could also be different. So in general, these numbers can float around. So therefore, you have to follow the rule about drawing the band diagram. You know that, how to draw band diagrams in presence of this, right? And generally, I'm not going through the details, you will have a band diagram, something like this. You can see the blue line, flat quasi-Fermi level. Do you see on the right-hand side, I have drawn the bulk region, and the continuity of the vacuum level eventually gives you a diagram like this. I'm sure all of you know by now how to draw a band diagram. Now, you see, in this particular case, the band is no longer flat. Band is no longer flat, and this has bended in a particular way because phi sub m is less than this phi sub s, and I have defined what those quantities are. Because this is one is bigger on this side, you can see it is sort of tilted towards the metal side. Had it been some other metal and some other semiconductor combination, it could have tilted the other way. So we cannot a priori say that which way it will tilt. But in general, let's start with one, and then we'll get the basic idea for this spatial case. Now for this spatial case, you realize that there is something very interesting here. First of all, even at zero bias, even when I haven't applied any gate bias, body is grounded, haven't applied anything on the gate. So first of all, you can see that phi sub s, the surface band bending, is no longer 0, right? Previously it was all flat. It has sort of bended down towards the oxide already. Therefore, if you look close to the surface, you will realize that not only the holes have been pushed back even at zero bias, and the whole thing has been depleted near to the surface, oxide semiconductor surface, but in addition, I have electron buildup on that corner. That green corner, the electron has built up. Why? More than the equilibrium one. Equilibrium one is Ni square over Na. That's the equilibrium one on the bulk side. But I have electron buildup, of course, through generation and on that corner. Now, do you realize that this doesn't happen in a diode? Why not? Why? What is in diode? If you have these two are metal semiconductor junction, right? And if you have bands like this, what will happen? It will happen. There will be depletion on one side, there will be depletion on the other side, and then essentially there will be a depletion region. We can calculate that. We know how to calculate it. There will not be a pocket of electrons piling up. That happens because we have an oxide here. An oxide acts like a dam. It doesn't let the electron go. When you had a diode, we didn't have a sort of a oxide or a dam sitting in between the p and n side, preventing the electrons to go. In that case, the green electrons will go to the other side and mingle with the electrons on the metal side. So this extra buildup is sort of unique for MOS configuration or MOSFET configuration. Do you realize why there is extra electron? Because you can see the conduction band has gotten closer to the Fermi level, and therefore you expect more electrons to be there and less holes. Okay. Now, let's ask ourselves this question. If I now start applying a gate bias, right? I want to invert this transistor. Do I need more or less gate voltage in order to invert it? Now, you can almost clearly see that you might need a little less, right? In this particular configuration, it's already sort of bended in the right way of how I want to bend it. I put a little bit more. I have 2 phi sub f surface band bending. I have my inversion point. So you can see immediately that my total amount of voltage needed to reach threshold will be a little less because of this band bending in this particular way. Now you realize, had it been the other way around, phi sub m being greater than phi sub s, in that case, I might have needed more because it had bended the opposite direction, and therefore I might have needed more to bring it back and invert it. So this is then extra factor, the phi ms, that sort of comes in the threshold voltage considerations. Now let's talk about what is this flat band voltage issue. Now physically, what flat band voltage means is the amount of gate voltage you have to apply in order to make the bands flat. That's flat band voltage. So which direction do you think we should go in order to make the bands flat? Vg is 0 now. Now, do you remember that when I apply a negative bias to a contact, it generally goes up. Apply a positive bias, it goes down, right? You remember that. So in that case, in order to make this band flat, which direction I have to go? I have to apply a negative bias. Exactly right. And that negative bias will make the whole thing flat, and that is called a flat band voltage. FB is for flat band. That's the small part of it. And this is telling me that the flat band voltage is equal to the difference of work function between metal and semiconductor, but also equal to this minus VBI. This is the same built-in potential that we have seen before. Do you remember? Diode, we have built-in potential, same. So let's calculate this, because once we calculate it, we'll know how far away from the idealized case are we, so that we can calculate the actual threshold voltage. So let's do that. Let's calculate what the VBI is. Now at this point, I shouldn't really have to even do anything. You should be able to calculate VBI for the left-hand side structure immediately, right? You know how to do it. So what do? I always have followed one single rule. And the rule to calculate VBI is essentially sum up the work function till the flat vacuum level part on the top on both sides, on the metal and semiconductor side. And you know what you have to write. Do you agree with this? On the right hand side, I have chi sub s, the semiconductor chi, the band gap, that's the Eg, and the delta P is what the Fermi level is with respect to the valence band, because that's the extra I have gone in that direction. And on the left hand side, I should have written phi sub m plus q VBI. That's what I should have written. And therefore, I have flipped it on the other side. And 1 second, I calculate what VBI is. Do I know everything here? Well, chi sub s and phi sub m, I can, given two materials, I immediately know them from the textbook or any reference book. Band gap, yes. Material known, band gap known. And delta P, well, that's if I know the doping. From the doping, I know how far away the Fermi level is. So I can easily calculate it. And that will give me the flat band voltage. And you should convince yourself that this flat band voltage is also the difference between the metal and semiconductor work functions, these two work functions. So I'll leave it as an exercise. It's a very simple thing. You can just see from this particular diagram. Therefore, if I know what my flat band voltage is, then you realize that my threshold voltage will now be reduced by this idealized threshold voltage. Remember, that's the first two term on the bottom, 2 phi sub f and qb at Cox. That's the idealized one. That must be reduced by the flat band voltage, because I already have that amount of voltage applied to the gate. And so therefore, I will need to apply a little less in order to invert it. Now you realize that if the flat band voltage went the other way, I had a negative sign, then I would have needed a more voltage to invert it. So as a result, this expression for the threshold voltage, because of this non-ideal effect, will be slightly different from what we have calculated before. But it's a very simple calculation. You can see, as soon as I tell you what the two materials are for the metal and the semiconductor, then you immediately know what this new threshold voltage would be, right? Now that's how you will calculate it. But how would you know what you calculate are right or not? First of all, you can punch wrong numbers in your calculator. That's one problem. The other is that many times you do not know whether there are other problems there or not. So many times what you have to do is to go ahead and make a measurement. And the measurement would be the capacitance divided by the oxide, normalized to the oxide capacitance. So you remember that on the left-hand side of this plot, these are accumulation. Accumulation charges are next to the oxide. It's a parallel plate capacitor, majority carriers from two sides. So therefore, you have a certain capacitance. And then as the oxide, as the semiconductor begins to deplete with positive bias, remember the holes are being pushed back, your capacitance begins to decrease, because you're essentially the total capacitance distance, the D, is larger than the original one. So therefore, it begins to decrease. What type of frequency do you think I am at? This is a MOS capacitor. This is high frequency. Absolutely. Absolutely. Because in that case, it didn't have time for the minority carriers to be generated and get the inversion charge respond to the small signal, right? So therefore, I have that. Now, threshold voltage, you all know how to calculate threshold voltage from this curve, right? The point where the curve essentially stops dropping and essentially becomes flat. At that point in the DC, the accumulation charge has formed. Only in the AC, the accumulation charge cannot respond. So therefore, it responds to the age of the depletion on two sides. That's why it becomes flat. So at that point, we call that the threshold voltage. That's my ideal threshold voltage. Now, again, from an experimentally measured curve, from the ideal threshold voltage, you should be able to calculate back what the bulk doping was. Remember 2 phi sub B, 2 phi sub B minus QB divided by Cox. So from that, you should be able to calculate what the bulk charge is from an experimental curve. Now, if you have a non-ideal device, then what's going to happen for the particular one that I just showed you, this whole oxide curve, this capacitance curve will shift to the left because I need less voltage to invert it. So therefore, the whole curve will shift to the left. Equally important, the transition between accumulation and depletion, that point will also change, right? Because it's already at zero gate bias, it's already sort of partly inverted or partly depleted. And so the whole thing, the whole curve will shift to the left. And now this becomes your threshold voltage. What is the difference between these two threshold voltages? That's the flat band voltage, or that's the built-in voltage, right? These two threshold voltage. In this particular case, the whole thing has shifted. And how do you determine the flat band voltage? Again, you can either do it by changing the threshold voltage, or you can look from the accumulation to depletion transition, the point where it goes from flat region to the depletion reduced capacitance part. So that can also tell you how much the flat band voltage you need in order to shift this curve. Okay, so that's one ideal effect, non-ideal effect that I have to take care of. But that's very simple. I mean, nothing could be simpler. Now, this next thing I want to tell you about is something that's really non-ideal, and this one depends on device to device. This is an issue about trap charges. Now, why is it that I didn't ever discuss any of these things in bipolar? Doesn't this thing happen in bipolar transistor? Certainly. It does happen over bipolar transistors also. The things that I'll be talking about does happen, but in many cases, bipolar is a vertical device, meaning current flows from the top to the bottom. And therefore, most of the time, it doesn't see surfaces. And most of the problem that I'm talking about has to do with surfaces where the charge gets injected, has to do with amorphous material where charge can be trapped because it's not crystalline, defects are present. So therefore, in many cases, these could be more dominant in MOSFET. MOSFET is a very sensitive device, you realize. 10, 20, 30 angstrom close to the surface, a thin layer of electrons moving from source to drain. That's all there is to it. And you can easily see that it may be perturbed by any imperfection on the surface. So therefore, this is a topic that people pay a lot of attention when they are designing MOSFETs. Again, let me remind you that this was the ideal one. And I'm trying to see what the non-ideality would be if there are charges, in the oxide. So the first thing I want to remind you that I didn't have any charge in the oxide. Now, is that really right? Is it that I'm not talking about, it's important to understand, not talking about electrons and holes in a traditional sense. Yes, silicon dioxide 9 eV, below the valence band in silicon dioxide, you have lots of electrons because these are silicon and oxygen. Of course, you have a lot of electrons. Conduction band is so far up, you know that the formula Ni squared, if you wanted to calculate Ni squared, it will be Nc Nv e to the power band gap over kT, right? Remember, band gap is 9 eV. So you have almost no free electron in a silicon dioxide. That's why it's insulated. So, of course, in an ideal insulator, you don't expect any conduction charges in there. And similarly, in other places, things were charge neutral. But the oxide charge I am talking about is not electrons and holes in the traditional chains. This is the charge that sort of come in from outside and sort of start residing within the oxide. So that's the extra charge we are talking about, nothing to do with the intrinsic semiconductor. Now, as soon as you put the extra charge, life becomes a little bit more complicated. Because first of all, you can see that even without charge, I have shown things as with having a band bending. Because, just what I told you about, the flat band voltage and all. And therefore, because the two work functions are not the same, you have a certain amount of band bending. You can see that here the threshold voltage will be a little lower, right, compared to before. In addition, look at the oxide and look at the oxide band, no longer a straight line. Why not? Because that if you didn't have a charge, whatever electric field came in, that same electric field went out. Because any dE dx, the change in the electric field, that is equal to charge. If you don't have any charge, you don't have any change in the electric field, a straight line. But if you have charge, now very important, notice where I have put the 0, the origin. The origin is always, for our calculations, it will always be starting from the metal oxide surface. Don't try to put 0 on the oxide semiconductor surface, because everything is reference to that point. So let's say I have some charges in. Now these charges, although I have drawn it within the band gap, this is really not within the gap in that sense. There are defect levels within the gap, just like remember copper, aluminum, they had defect levels in the silicon. Similarly, there are defect levels and the electrons and holes are sitting within those defect levels. That's why the charge is. Now, if you have that charge, as a result, you can see that your electric field within the oxide will be changing, and therefore you have a non-uniform potential within that region. So I'm going to define a few quantities, and then I'm going to go through and calculate what the extra effect of that charge is. So the first thing I want to define is the area under the curve. So let's say I have a certain amount of charge. The ordinate of that curve is rho O sub OX. This is at every point how much charge you have. That is like number per centimeter cube, right? So density, you have certain amount of charge. The area under the curve, I will call that QM, Q sub M. There is a historical reason. What does M mean? So there is a historical reason why the word M is used, because historically in 1960s, there is a great drama, and I'm going to talk about that a little later, about mobile charges being present in the oxide. In fact, that almost killed the MOSFET program. Remember, MOSFET was actually patented before bipolar transistor. MOSFET was patented in 1920s. But it happened much later. My actual MOSFET, operational MOSFET is in 1970s. Bipolar happened before that, right? 1950s. So the reason that happened and how the engineers in Fairchild Semiconductor, this treacherous 8 I always tell you about, right? Who defected from Shockley Semiconductor and went and built their own company, joined Fairchild. They, in fact, that series of 5 and 6 years, beautifully solved many MOSFET problems. And one problem they solved was about mobile charges. So although these charges in modern context is no longer mobile, this symbol M still persists from those days. And I'll explain to that. It's a beautiful story. But QM is area under the curve, And this chi sub M is sort of the moment of the charge. That if you had to replace all these charges with a delta charge at some point, effectively, then where would you put it? You will put it at X sub M somewhere, and I'll show you how to calculate that. But the way it's done, you can see the numerator has the first moment of the charge, and the denominator has the total charge divided by X0. X0 is oxide thickness. So I will show you how to calculate chi sub m or x sub m in a second. But this is the general framework. Let's say I can calculate it. I mean, you know, the prescription is clear. If I told you rho oxide charges, you can do this integral, right? No problem. You can do this, and then once you have done it, the extra change in the threshold voltage, extra change will be the ideal one, which is the first two terms, right? Phi sub s and qf divided by Cox, and then, I'm sorry, that should be qb divided by Cox, and this extra charge is what's going to cause a change in the threshold voltage, right? Now, why is it? Physically, why does threshold voltage change? I could previously see band bending, so that's why I have a change in the threshold voltage. Let's try to understand first and then calculate. So, in this very colorful plot, so I have drawn the yellow depletion region. This is the charges depleted of what? Depleted of holes. Holes have been pushed back. So, I have applied a certain amount of gate bias, and you can see the positive gate bias in green has resulted in some sort of positive charge. And this charge is being balanced by the yellow, which is the depletion charge, and this, what is that color? Huh? This reddish color or something. And that color, the sum of these two is equal to the green area under the curve, right? This charge must be balanced. Now, you know how to calculate the electric field in this context? Of course, you just do the area under the curve and you're done. Do you agree with this statement that the electric field, so you'll have to start from the right, let's say, go through the yellow is a constant region, so the integral is a constant part. As soon as you hit the inversion charge, the total amount of electric field goes up, jumps up, and then in the oxide, I have no charge, idealized case, remains flat. Not exactly, so there has to be a discontinuity by the amount of the two dielectric constants. Remember, the electric field will change there by the dielectric constants. And you go to the green side, and it sinks all the electric field, and it goes back to zero. Idealized case. So we know how this happens. Okay. Now it's minus E, because when you do the charge integral, you remember this is negative charge, so you have to do in a particular way. Okay. Now, what would have happened? What would have happened if I now have some bulk charges or all charges within the oxide? So you can see something else has to happen. So let's say I put some extra positive charges in there. First of all, do you realize that in this case, if I look at the charge balance, the green has to be a little less, will need to be a little less. Why? Because the green and a blue together is a positive charge, yellow and the red together are negative charges. If I am at threshold, if I want to go at a particular level of inversion above threshold, then the yellow and the red must have a particular value. Now the green will take care of a little bit, and therefore I will need a little less green, the blue will take care of a little bit, and therefore I will need a little less green. As a result, I will actually need a little less gate voltage to invert this transistor, because the sort of the blue, the trapped charge is helping me to invert, right? So you can immediately see that there will be my threshold voltage because of the blue charge trapped within the oxide will be a little less physically. I mean, there's no math here. And you can sort of make that argument that if you wanted to look at what voltage you need, the voltage is always the area under the electric field. By the way, do you agree with my drawing of the electric field diagram? The yellow part a constant, jump near the inversion, then the electric field continues. I should have made it discontinuous by the dielectric constant, but apart from that, and when it hits the blue, then it goes down, the total amount of charge goes down, and then when it hits the green, it goes to zero. So area under this curve, which gives you the voltage, area under this curve, electric field curve gives you the voltage. Do you agree that this is a little less than the idealized case? And therefore, for the same level of inversion, you need a little less voltage. And that's why the threshold voltage is a little less for this positive case. Had this blue been negative, it would have gone the other way, right? You realize that. Now you also should realize that it really matters where the blue charge is, because if the blue charge is, I've shown here in red, if that is close to the surface, do you see the consequence of that? The consequence of that is that that charge, if the trap charge, if it is closer to the surface, it has even a stronger impact. Look at this. The yellow region we integrate goes, straight, goes up on the inversion charge, but the interface charge that I have immediately brings it down. And then, of course, it remains constant and goes away with the green. Now, the green, in this case, I will need even less, because area under this curve, area under the electric field curve, what is that? That's the voltage. So, that voltage is much less than the ideal one. So, the bottom line is that, first of all, trap charges reduces the threshold if it is positive in this particular case. Second is that closer it's to the interface, more effect it has, right? These two things will, of course, come out in the math also, as I'll show you in the next slide. One thing before I go from here, now I'm making everything with respect to a N-type a P-type semiconductor, Now, if I inverted it, gave you a problem where things are in N-type, you cannot just copy from here. You have to look at the total amount of charge, look at the sign of the blue, and keep the depletion and the inversion charge is the same. That's your boundary condition. And then correspondingly adjust things, right? Always start integrating from electric field from the right side, not from the left side, because the right side is a constant. You want a certain amount of current, and then you are trying to calculate what gate voltage will give you that current. So that certain amount of current is given by this red inversion region. So therefore, you have to start integrating from the right. Don't start from the left, because that will give you a certain gate voltage, but a different amount of current, something that we don't want to calculate. So let's calculate then. A few lines of math, very easy. The gate voltage is equal to the drop in the oxide voltage and vice versa. Before, my life was simple. Vox was electric field multiplied by x naught, and I went home. This time, well, I'll have to write the Poisson equation. So I write the Poisson equation, the second derivative of the potential with respect to x, that's equal to rho oxide charge inside. Previously it was 0, so therefore I had a constant electric field, but this time it's not 0, so therefore I'll need to integrate. I'll need to integrate from x naught. X naught is the right side boundary of the oxide from any x at any given x, and I integrate on both sides. This is all happening within the oxide, so you can see the kappa ox, right? That's the dielectric constant. So you can see that. So that's the first integration. You put the limits in for the electric field. That's the first integration. And then if you want to do the second integration, because I really want Vox. If I want to do the second integration, then I will integrate one more time. What's there to it? There's nothing much. Eox at x naught, that's a constant value. I know that. That's coming from the inversion charge and the depletion charge, right? The yellow and the red, the sum of that. So I know that. That's a constant. So when I integrate, it goes out of the integral and I pick up an x naught. So I pick up an x naught, and the second one I have a double integral. Now I again leave it as an exercise to show that the double integral can be reduced to that first, second single integral. Below there, only thing is that you pick up an x multiplying that rho ox, right? That's the extra thing that you pick up. Now, do you realize the first term of Vox is what I had before when I didn't have a charge in the oxide? What would have happened if my rho ox is 0? Second term wouldn't exist, right? First term would be there. It was always there. So the only extra thing I have picked up is the second term because of this extra blue charge that I have within the oxide. And again, this one sort of, does it make sense to you? That you can see now, if X is large, if the charge from the left side interface is farther out from the left interface, the effect is more, right? You can see that that's why if the charge is close to the semiconductor oxide interface, then the effect is actually more. And that's already coming through this math, what we physically and intuitively already knew. So you can calculate this, and this is the ideal part. That's, we have done this before, and this is the extra thing. This extra thing, if you remember the definition of chi sub m that I had, this is a one line of algebra that tells you that if you have fixed charge, the Q sub m within the oxide, then your threshold voltage will be shifted by this extra amount. It sort of makes sense because the charges either help you to invert a little earlier or hinder to invert a little later. So that's essentially the physics of it. Again, you can do the same CV characteristics, and from that can calculate this extra amount of charge to be present. Now you can ask that what would have happened if both there is phi m of non-ideality from the metal semiconductor work function and non-ideality from Q sub m. Both would have caused a shift in similar amount. How do you decouple them? So I'll ask you to think about it, and then in the next class I'll tell you what to think, what the answer is. But the point is, from the CV characteristics, by looking at the change in the threshold voltage, one should be able to pick up these charges. Okay. Now, if you have interface charge, then I can again use that formula, but there is this dreaded delta x minus x naught, which you have seen also in Schrodinger equation, right? That if your charge is actually a delta function, by the way, it cannot be rho ox anymore. If you have x minus x naught, then you realize that that should be charge. It's no longer per centimeter cube when you have the delta. So apart from the dimensional change, what should be the whole thing you can pick up, and the rho ox at the interface, that will be the Q sub f and multiplied by x naught, and that x naught will cancel the x naught outside, and you will have this CO, the oxide capacitance. So if charges are next to the interface, then we have this very simple formula where we divide the fixed charge by the oxide capacitance. I don't have to calculate any moment or anything. I can immediately get the full effect in the threshold voltage. So that's many times in the interface charge this is done. Now these charges I'm talking about, like trapped holes within the oxide. So I'll show you later where the trapped holes come from. Okay. Now this is what I was trying to tell you about 1960s and the time-dependent shift of charges. So, and the experiment is in next slide, but the essential point is this. You expect that when you make a MOSFET, you expect a IV characteristics. Now let's say in the morning you came to work and you measured the IV characteristics. You expect that you go to lunch and come back, your IV is where it was before. If you make the second measurement, where it was before. But after lunch, if you see that your IV is completely shifted, is completely in a different place, that does not mean you did anything wrong with the lunch. Lunch was fine. The MOSFET, there is something funny going on in the MOSFET. And this was a big problem. It's called a bias temperature instability, BTI. And in 1960s, it drove people crazy because what they saw, that they would make a measurement in the morning, same device a little bit later would have a completely different characteristics. Of course, you cannot make a microprocessor like that, right? In the morning it's working, in the afternoon it's not working. Not very good microprocessor. But, so there was a great detective story. You can read it, but essentially what people found out, that the charges from this within the oxide actually was moving back and forth, moving back and forth. So this charge in the morning, you start the charge there. Now your threshold voltage, as you have applied, so this is as a function of time. In the morning, let's say the charge was next to the green. And then you went to lunch putting this oxide in the measurement setup, and this blue charge would be moving as you are during lunchtime. And therefore, as it goes to the other side, you can see that now this x1t, where the delta charge is no longer at the same place. Therefore, your threshold voltage throughout your lunch period is actually your threshold voltage is changing. If your threshold voltage is changing, then the amount of inversion charge, you have the same gate bias, right? You set it up. So therefore, your same gate bias, but your threshold voltage is changing. What will happen to your current? Your current will keep going down because threshold voltage is increasing. So your current will keep going down, and that would be a big problem, right? So this turned out to be, and also if you come back and apply a negative bias, the charges will go to the other side. The blue will start going to the other side, and the CV will do this oscillation going back and forth. So that's a very big problem, and it turned out that this is sodium. Sodium, many times people in those days didn't know that they have to use gloves in the clean room and all those. And in our hand, there's this sodium and the sodium chloride. So anytime you touch these wafers with bare hand, right, then what happens? Sodium from the hand gets into the wafer, and that resides in the oxide. And the sodium is a small atom. It's an amorphous material. So it finds its path going back and forth. Sodium is a positive atom, right? So as soon as you apply a positive voltage, it doesn't want to stay close, and so it's pushed back. You apply a negative bias, the sodium comes back. And so this oscillation goes back and forth. Bias temperature instability, because if you raise the temperature, this happens faster. And so this was a big problem. And eventually it was solved simply by putting on more cleaner condition and putting some globes on. These are the experiments. So you can see in the morning, that's the right-hand plots, and it can shift as much as 80 volts. Of course, those days oxides were thick also, 1000 angstrom oxide. So huge shift. And essentially, this would cause a significant problem. And so the point I wanted to make, this is something you will find in your textbook also, that depending on the applied bias, if we apply a negative bias, the sodium will get close to the metal oxide surface, and you can see in the blue. And then if we apply a positive bias, then the sodium will get to the other side. And then therefore, depending on the charge, where this charge is, of course, you realize that the threshold voltage will be different. And as a result, you can see the threshold voltage moving back and forth. By the way, what type of substrate is this? Can you say from this, just looking at this picture? All my CV curve, I had been drawing in a particular direction, right? So what type of substrate is this? This is an N-type substrate. This is an N-type substrate, right? The CV is going the other way. Do you see? So can you calculate from here the flat band voltage, the threshold voltage, all those things? Can you do that? You should be able to do that. Can you also calculate how much sodium was there? But just by looking at the total amount of shift in the threshold voltage. Certainly you can do that, because when it's stabilized on the other side, it sort of charges moved from one side to the other side. And so the total amount of shift, essentially you can calculate from the shift in the threshold voltage. You should be able to do all those things because I just told you how to do it.